Recording is in progress, and we are going to tackle some solutions, which kind of sounds tough because a solution is kind of a liquid and can't really tackle one. I mean, if you do, it would kind of spill everywhere. At any rate, we're going to get into our discussion of solutions. We're going to kind of elaborate on what we talked about last time and go into a little bit more detail. We got a couple of top hat questions, and yeah, this will set us up for a nice weekend. And you've got three quizzes on Canvas. Those are due on Sunday at 11 p.m. You got two attempts at each of them, and you got 15 minutes for each. So go get them. Now, with that said, we've got some stuff. I'm just going to bring this back and I can breeze through it. You got your solvent and solute. Typically, water is the solvent because it's the universal solvent. Now, we talked a lot about concentrations of solutions. If you remember, we had the discussion about, well, Kool-Aid, lemonade, Capri Suns, whatever. If there's a lot of drink mix to a little bit of a solution, so a lot of solute to a little bit of solvent, well, then that's going to make for a really tasty and intense Kool-Aid experience. If there's a lot of water to a very small amount of Kool-Aid or drink mix, that's going to make for, do I even taste it? Is it there? Yeah, it is. Okay. We played around with some demonstrations where we looked at concentration. And then we got to the units and our units of molarity. Well, molarity is our unit for measuring concentration. And this is moles of a solute divided by liters of solution. Okay, so what this means and where this goes is, if you see a question like 35, let's say 35 grams of NaCl in a solution with a total volume of 6 liters. My question for you is this ready to go? Are we ready to do this calculation and determine the molarity of this? And I know that you might be thinking, well, yeah, all that I need to do is I need to take the mass and convert it to moles. You're right. And that's where I was going. That's kind of what I was wanting you to basically look at and answer. Because that's what you need. You need 35 grams and you need to convert that to number of moles. How would you do that? Well, you have to go to the periodic table and use the molar mass. So if you have the number of moles, so I think that the molar mass of NaCl is about 58.4 grams. So 35 grams, that's a little bit more than half. I'm going to call that like 0.6 uh, moles in 6 liters. What's the molarity of this solution? Well, 0.6 divided by 6 is going to be 0.1 molar. Awesome. Perfect. That's what we needed. Now, one of the points there is that you can't go from just mass, NaCl, you have to convert that into moles because moles are the language that chemists speak and the terms that chemists use. So you need to be able to, kind of play in that domain. Now here we played around with adjusting the solution volume, going up, going down, and seeing how the concentration of the solution changed. So here is our first top hat question. I'm going to toggle it over to the top hat entry because you put that in right now. But what is the molarity of a solution made by dissolving 2 moles of NaCl in enough water to produce 0.5 liters of solution? Now, before I turn it over to top hat settings, and you can answer it, I want to draw your attention to this wording. It seems a little bit funky. So 2 moles of NaCl in enough water to produce 0.5 liters. In enough water. That sounds almost like the amount of water you don't know what it is. That's kind of how it sounds to me. Um, but remember, and this is kind of this is like a subtlety of this calculation. Moles of solute, that's solute, divided by liters. Well, just a second, Aurelia. Um, liters of solution. Now, my question, or the reason that this has kind of a funky wording is because if you were to make, or if you were to get 2 moles of NaCl and you were to add to that 0.5 liters or 500 milliliters, and you put that into a graduated cylinder, let's say this is 500. Does does salt take up space? Sure, it will dissolve, but does it take up some space? It absolutely does. So if I got, let's say that I got 500 milliliters or zero point 0.5 liters of water and I added it directly to here. And then after that, I got the salt and added it to there. Chances are that with the salt added, do a little erasey here, my volume is actually going to be like up here. The reason is because NaCl occupies space. So that's why we have this kind of what seems like strange phrasing, because you kind of have to like you would get the solid and then you'd add water up until 500 milliliters. Are you adding exactly 500 milliliters of water? No, you're adding like 490 or something. But the salt does occupy space. Okay, so now let's go back to our calculation. 2 moles of NaCl in enough water to produce 0.5 liters of solution. We got this as a top hat question. I'm going to clear all my drawings out. And let's go ahead and answer that. Let's see what we got. We got 19 answers. 2 divided by 0.5 is 4. I'm going to plug this into my calculator, make sure that I'm feeling good about that. 2 divided by 0.5. 4 is our correct answer. So the concentration of this, there's 2 moles per 0.5 liters. So one way that you could do this is you could say, let me use my, I mean, you can plug it into your calculator, but a way that I always like to think about this kind of logically is I'm going to say, all right, well, molarity is moles per liter. Well, this is number of moles per 1 liter. How would I get 0.5 to equal 1? I multiply it by 2. So if I multiply the bottom half of this by 2, what should I do to the top half? I should also multiply that by 2. And that's going to give me 4 over 1. That's one way that you can approach this. If you don't have a calculator handy, that's how you can deal with it. Okay, now another top hat question. Let's use the same sort of thing. But here we've got, what is the molarity of a solution made by dissolving 10 grams of NaCl in enough water to produce a 1 liter solution. Okay, so 10 grams, and I'll give you this so that you can use it. I'm going to put it on the next slide, or write this number down. 1 mole NaCl is equal to 58.4 grams of NaCl. So effectively, the way that we want to do this calculation is 10 grams NaCl, 58.4 grams of NaCl, and 1 mole NaCl. 10 divided by 58.4. Do that, and that will get you the number of moles of NaCl. So now I'm going to go ahead and open this question up. So I'll leave that on there, actually, as the math that you need to do. 10 divided by 58.4. You got a full minute for this question. All right. 10 divided by 58.4. Let's do this. 10 divided by 58.4 is 0.172 or 0.17. So 10 divided by 58.4, that gives you the number of moles. 0.17 moles divided by 1 is going to be 0.17. Which one of those is closest to 0.17? 0.2. 0.2 is the correct answer for this. So you need to do 10 divided by 58.4 because you need to take the mass that is provided to you and divide it by the molar mass to figure out the number of moles. Okay, now we got another shot at this. What mass? This is kind of taking similar questions, but contorting it a little bit. Okay, so let's go through this one pretty deliberately. I'm going to clear, you know what? I'm not going to clear all my drawings. Yeah, I'm not going to clear all my drawings, but what I'm going to do is erase this. Okay. So my question is, what mass of NaCl is required to prepare 0.5 liters of a 2-molar solution? Okay. So essentially what we need is, here I'm going to draw a beaker, and don't answer this one quite yet, anyone. We need 500 milliliters of a solution that is 2M. Now, not thinking about our solution, the volume of our solution, we know that 2M is 2 moles per 1 liter. Okay. So let's think about this. If we have a solution that is 2 moles per 1 liter, how many moles are in half a liter? Answer that in the chat. If it's 2 moles in 1 liter, how many moles are in half a liter? Perfect, Joey. Protozoan, perfect. Absolutely, it's 1 mole. Okay. So now my question for you guys is, If this is the number of grams that constitute 1 mole, well, let's do this. We got a full minute for this. Okay, we got 20 answers in. Let's see what we got. Great job, everyone. That's pretty darn good. So our process here was we took the volume, zero point 0.5 liters. And what we did, or what you can do with this, is multiply your volume by the concentration, because that gives you the number of moles that you need. And in this case, it was a simple, well, 1 mole. And by us knowing the molar mass of NaCl, we knew that the answer was 58.4. So a process for this sort of question would be multiply volume by concentration to get number of moles. And as soon as you have the number of moles, then you can say, well, do I need exactly 1 mole? Do I need half a mole? Do I need 2 moles? As soon as you've done that calculation, multiplying the volume by the concentration, you'll be able to answer that question. Okay. So the next sort of thing related to, and if that was a tough question, which those last few were pretty challenging, what I would recommend is to kind of repeat those questions. Now, this next type of question is known as a dilution. So in order to do a dilution, you have a simple equation. And this equation is M1V1 equals M2V2. Some people also mention it as C1V1 equals C2V2. Now, when it comes to M1V1 equals M2V2 and C1V1 equals C2V2, they mean the same thing. The V stands for volume, and the M stands for molarity, and the C stands for concentration. But they effectively mean the same thing. Now, I think that another way to think about this is to think about it as the 1 is initial, and the 2 is final. So in this case, what you would see is something like, I have a solution with a concentration of 0.3 molar. I want to make 500 milliliters of a 0.23 molar solution. Okay. Now, what you should notice there is our initial concentration. So the solution with a concentration, so the solution that we described has a concentration of 0.3 molar. Okay, so that's where we started. And then our second solution had a concentration of 0.23 molar. So our concentration went down. Okay, that means we diluted it. We added water to it effectively. Now, if we have, the question here is, well, how do we do that? So what we would do in order to set up the equation, we would say our initial concentration or our initial molarity, 0.3 molar times V1 equals 0.23 molar times 500 milliliters. This V1 is going to tell us a volume that we need to take from, so this would be our 0.3 molar solution. And this right here is our, as of now, non-existent 0.23 molar solution. So what volume, what V1 do we need to take from this solution? Is it 5 milliliters? Is it 200 milliliters? We don't know, but we're going to find it out. And when we take it from there, we're going to put it in here. So this gives us a way to calculate by saying, all right, 0.23 times 500. 0.23 times 500 is 115. And we don't need to worry too much about that number because it's a very temporary number. Because what we're going to do is we're going to divide each side by 0.3. And that will give us our V1. So 115 divided by 0.3 is going to give us our V1, which is 383.3. So what that means is we would need to take 383 milliliters from our first solution and add it to our other beaker. And so we've added, so plus 383.3. Okay. Now, what would we then need to do? Here's the thing. We want our new solution to have a final volume of 500 milliliters. So how would we get 383 milliliters up to 500 milliliters? What do you add to a solution to dilute it? What do you add to super strong Kool-Aid to make it not so super strong? Water. Absolutely, Ryan. So we are going to add water. Okay. Now, if our V2, our total volume of that final mixture is 500 milliliters, do you have an idea of how much water we would need to add? Well, what we can do is we can say 500 minus 383.3. 117. Perfect, Ryan. That's absolutely right. Yeah, absolutely, Kaylee. So we need to add about 117 milliliters of water to this mixture. And by adding water, we've diluted it. How much do we dilute it down to? We diluted it down to 0.23 molar. So that's what this calculation is, where you start with a solution, you take a certain volume from it, and then you add water to that to get a new solution with a diluted concentration or a lower concentration. Now, this is a sort of question that it is like using this equation, most people feel comfortable doing that. But where it gets tricky is in what is the question that's being asked. So, yeah. So the way that these questions can be asked varies a little bit. I'm going to clear all my drawings here. Um, the question could be, and I'm going to put the text up. The question could be, how much of your initial solution is needed? That's one way. An alternative is, how much water is needed to make need how much water must be added to reach your final concentration. So if you had questions like this, how much of your initial solution is needed? Well, that that would be 383.3. How much water must be added to your final concentration? Well, that's your 117. This is where people, and whenever I say people, I'm referring to a younger version of me. Whenever I was first taking a class like this, um, I'd do the calculation and I'd be like, good, I'm done. It's awesome. I did it. And I'd put the number down, and the question would be this right here. And I would put 383, in which case I'd be wrong because I didn't get it right, because I did not read the question. I did the calculation and I thought, I'm done. Don't need to worry about this. So that's one thing that you've got to be cautious about whenever you're looking at dilutions and dealing with a solution dilution. That's always a funny term or phrase, but solution dilution. Okay, so next up, and this is our last thing for today, percent concentration. Well, if you went around your home or maybe your workplace, you'd probably find some examples of percent concentrations. So this is not dealing in terms of molarity, but instead looking at a different metric and different measurement. There are two major percent solutions. There's percent by volume. There's also percent by mass. Now, with percent by volume, what you've got is the volume of your solute and the volume of your solution. Okay. Now, one good example of this would be rubbing alcohol, or another example that, um, or another example would be beer. Beer is approximately 5.4%. And that's effectively a measure of, well, how much of that is ethanol? How much of that total mixture is actually ethanol? About 5.4% of it. Now, harder liquors like Everclear or something like that. If I remember correctly, an Everclear bottle on the side of it says something like 180 proof. Proof is a different measurement and not something that I'm going to test you on, but effectively that's 180 out of 200. So that's effectively 90%. So I always kind of look at those numbers. I think that it's worth looking at. 5.4% versus 90%. That's one of the reasons that people, if they drink beer, if they choose to drink beer, um, or alcohol at all, they might drink a can of a beer. They're not going to drink a can of Everclear because that would effectively be nearly the same as what would that 18 beers? If you had a can of Everclear, that would be like the same as drinking 18 beers. So bad idea. Um, Now I don't think that I apologize if that was a controversial subject, alcohol, but it's just something that's a measurement that does exist and that you can see at the grocery store. Um, Rubbing alcohol is a good example, though. 70% rubbing alcohol. You might also see 30% or 95%. And effectively, what that means is that you got ethanol, and if you had 95% ethanol or 95% rubbing alcohol or acetone or something like that, you're looking at 95 milliliters being pure ethanol and 5 milliliters being water because it's a volume by volume ratio. Now, if you take something like hydrogen peroxide or bleach as another example, bleach, if I remember correctly, is like 8.25%. That 8.25% being the active ingredient, the sodium hypochlorite. That 8.25% is going to be the mass of your solute. So in this case, that would mean 8.25 grams of bleach is dissolved in a total of 100 grams of solution. So when you're doing a mass calculation, you do determine the mass of your solution, the total. So you would effectively what you would do here is here's my digital balance, numbers 9.54. And then on your digital balance, you're going to put a beaker. And you're going to put 8.25 grams of bleach. And I got to go back and rephrase this 8.25 grams. Then what you're going to do is you're going to add water. And I say water because it's the universal solvent. You're going to add water until on the digital balance, it reads 100.00. When it reads 100, then you have reached your complete solution. Now, a very fair question there is, what is the volume measurement going to be? So what will the volume measurement be? And then another question is, how much water did you add? Well, you might only add a total of 95 milliliters of water. Does that make this solution wrong? No, because a percent mass solution is the mass of the solute divided by the total mass of the solution. So you might end up adding 97.2 milliliters of water. And then if you look at the bottle or the beaker, it might actually read 101.6 milliliters. Oh, what's with the discrepancy there? Why? Well, one thing is that your total volume of water that's added, well, that's just water. The next thing is that the bleach does occupy space. So that will take up volume. That will add to the total volume. So these two equations right here. Oh, darn it. I want you to know these two equations, and I want you to be able to calculate these things. Know that what matters whenever you're calculating a concentration, whether it's molarity or percentage, it's the total solution, not the specific amount of water. Okay. So that's what I have to say for today. Um, I'm going to go ahead and stop my recording. Thank you guys so much for coming to class. You've got 3 quizzes that are due on Sunday at 11.